got a bunch of correct answers out there. And we're going to go over this super quick. We got 3 things to do today. Okay. So look at, real quick, we got conservation of energy, right? E1 equals E2, where E1 is the energy up here at the top of the hill, and E2 is the energy down here at the bottom of the hill. Now, when we're talking about this energy, it's specific to mechanical energy, which is the sum total of kinetic plus gravitational potential plus elastic potential. And I think it's best if we put every single one of those types of energy up there to begin with. Now, is there kinetic energy up here at the top of the hill? Yeah, because it's moving. Clearly, there's gravitational potential because there's a height, and clearly there is no elastic energy anyplace in here. So kinetic energy 1 plus gravitational at 1 equals, now, is there speed down here at the bottom? Yeah, it wouldn't be much of a roller coaster if there wasn't. So therefore, there's kinetic energy down here at the bottom. Is there a height down here at the bottom? No. Right? And then there's clearly no elasticity. Okay? So if there's no energy that has been lost, how fast is the car going at the bottom of the first hill? That's camouflaged in here. 1/2 mv2 squared. 1/2 mv1 squared plus m times g times h1. Now, what helps our math here? Well, let's clean this thing up a little bit. Right? Birthday girl? Yeah, get rid of the m because there's an m in every single term. So that 1/2 v1 squared plus g times h1 must equal 1/2 v2 squared. How do I get rid of this half? Multiply by 2. Square root that whole thing, and I get my answer for V2, which I think if you put the numbers in there, came out to be like 28.1 something or something. Is that right? Okay. All right. So now, let's take that and let's go a little bit step further. Okay? If we go a little step further, then it's going to involve the idea of our roller coaster right over there, okay? If I take that little roller coaster setup over here, and the ball. All right, so look, Jack, ready? If I take the ball and I drop it off in here, does that go around the circle? I'm going to get it to go around the circle. Let's move it up. Get more around the circle, but not quite. I thought you were ready.
I thought I was ready too.
More around the circle, but not really kind of dropped off the circle. Did it stay on the circle the whole time there yet? Not yet. Still not yet. Right? It's losing contact with everything up here. Oh my goodness. So we're getting closer, we're getting closer. Still not there yet. Maybe a little bit higher. Here it is. Right here is the minimum height that this thing can make it around the circle without coming off the circle. Go to the lab table with some pens. Figure out that height. Figure out the minimum height that the ball can go and not leave the circle. Okay, listen, I gotta say that I've been thoroughly impressed so far today. Not just from this class, but the first class, right? So, like, never did I think we would get to the stage we are in 10 minutes. All right. So that's a testament to you. Your algebra, on the other hand, Perhaps not so much, right? But the idea of what you have to do, all four groups were right on. Now, some groups started a little bit differently, but in essence, they started, everything turned out correct. So, like, if I recall, did you start off over here, or did you start off over here? Oh, okay. So I would advocate for that being the way to do it, right? We got our conservation of energy set up right here. We got potential at the top, equal to kinetic and potential up here at this, what's it called, all right? Now, what are we looking for? We are looking for this height. So that algebraically, you can reduce it to involve this height right here and the velocity up here. And then the velocity up here is where we got to take our circular motion stuff and bring it into play. Right? Now, the same mistake was made by at least one of the groups that got made quite a bit in our last exam. Look, the sum of the forces equals mv squared over r. Up at the top, it's normal force plus the weight. But when the ball barely makes it around the circle, what's the value of the normal force? 0. We had lots of people randomly putting in the weight is equal to the normal force, which gives 2 times the weight over here. That's not correct. So here we got the weight providing the centripetal force to keep the object in the circle, ultimately giving this velocity equal to the square root of g times r. I bring that over here, and ultimately I would get 1/2 r plus the height of this thing. What's the height at the top of the ramp? 2 r's. Which means, how high do we have to drop that thing? We've got to drop it an amount equal to 5 halves r, which is 2.5 times. That is really well done for everybody. If you look at your algebraic expression that I left this side of the room with, it's essentially 5 halves r if you do everything correct. Right? So that's a really nice job. Right? Now let's return to our desk and add friction to this whole thing. Return to our desk and add friction to this whole thing. You will. Okay, so, all right, so look, if I use this roller coaster over here to go back to our original stuff, you're at the top of the first hill of Viper, you go down to the bottom. You start at the top, go at third speed, you go down to the bottom. In our setup here, we ended up with a speed of 28.1 meters per second. Right? Now, what happens is that if I take this battery and I roll it down, I set it down this thing. Not quite the exact same thing. Whoa, those are not going to end up with gas that's taking it all the way around the circle, barely makes it down to the bottom. How come? Friction. So let's think about this. First off, remember, mechanical energy is the sum of kinetic plus gravitational potential energy plus elastic potential energy. And when we know if energy is conserved, the sum of all of those things is the same, that every single time. Now, if the battery, let's pretend that it's got the same mass as the ball, it's about the same, right? If I drop the ball from up here, it starts with a certain amount of energy. If this battery's got the same mass, does it start with the same amount of energy? Yeah? What's the mechanical energy bit right now? Yeah, but like if we use the bottom of this track to be the baseline, then its height is zero. It's got no speed, so it's got no kinetic energy, and it's got no elasticity. So it started with energy up here, and it ended with no energy. What's the change in mechanical energy? Yeah. What's the only way we can get a change in mechanical energy? What? Oh, yeah. Let's take one step further back. And we'll get to that next step. There definitely was a force. Well, let's just combine those things. The force did what? Work. Remember our main principle from last week? What was our main principle from last week? The only way to change the mechanical energy of a system was to do work. So if there was mechanical energy up here, and there is no more mechanical energy down here, there must have been a change in energy. So work must have been done from outside the system. What did the work? Friction does the work. When friction does work on a system, it takes mechanical energy away. Where does it go? Oh, four-letter word. Goes to heat. Heat's a type of what? Energy. Is it a type of mechanical energy? No. Right? So there's a difference between that overall conservation of energy philosophy that you did in like elementary school, right? Energy can be created sort of. That's different than what we're talking about. We're talking about conservation of mechanical energy. So when friction acts on a system, some or all of the mechanical energy gets converted to heat. So when friction acts on a system, there's a decrease in mechanical energy, and any mechanical energy that's lost gets turned into heat. Now, these are posted out of the school, by the way, so you don't have to copy them now. If we factor friction into this setup, and we say that friction does 25,000 joules of work, how fast is the current now going at the bottom of the hill? Well, before we go any place further, birthday girl, what do you know about the answer to this question compared to this? Now relax. There's a couple different reasons. At least, Grace, what's one of the reasons? Was that? Okay, more specific than friction. What does friction do? Friction opposes motion. Its job is to slow things down. From an energy perspective, the answer to that question would be friction does work on the object, taking the energy away from the system. So I can no longer write, I basically still got the same picture, but I can't write E1 equals E2 anymore. I need a different mathematical symbol in there. What mathematical symbol goes in there? E1 is greater than E2. E1 is greater than E2. How do I make it an equal again? So, plus change in energy. Love it. E1 equals E2 plus the change in energy. Well, what's the change in energy equal to? Yeah, numerically it's 25,000 joules. Algebraically, or like in some people could read, the work done by friction. Now listen, here's the common error, misconception, misstep. People love to just put the force of friction in here. Remember, work and energy are basically equivalent to each other. forces are not equivalent to energy or work. So it's the work done by friction, not just friction. Yeah? All right, well, how fast is this thing going up the end? Well, we got to go through the same process, right? Well, look, let's skip a step, but basically, what types of energy do we have up here? Gravitational potential and kinetic. I got kinetic down here. So along those regards, I got kinetic at 1 plus gravitational at 1 equals kinetic at 2 plus the work done by friction. Now look, that is the equivalent step to right here. Look at over here. Kinetic plus potential equals kinetic. Well, here it's kinetic plus potential equals kinetic plus the work done by friction. Now look, has the left side of this equation changed at all? No. So if I had 100 units of energy over here, I know I'm making that number up. I got 100 over here. Well, all 100 equals the kinetic energy down at the bottom of the hill. But now all 100 can't equal the kinetic energy because I got this other term. Which means what had to happen to the kinetic energy at 2? Got to go down, which means its speed goes down. Well, if we got to find this speed again, we got to get rid of this work done by friction from the right side. How do we do that? Subtract it over. So I've got kinetic energy plus gravitational minus the work done by friction equals K2. M times G times H1 plus 1 half mv. No. Just got it in order. 1 half mv1 squared plus mgh1 minus the work done by friction equals 1 half mv2 squared. That's basically the same stuff as this thing right here. What was that next algebraic step right here? To get rid of what? The m's. And why can we get rid of the m's, Lauren? Every term had an m. Can we get rid of the m's here? What doesn't have an m? The work done by friction. Now, in addition, right, like I kind of skipped some steps because I know what this problem is. Notice, I broke the kinetic energy down. The reason I did that is because the problem does not tell me a number for kinetic energy. I broke potential energy down. How come? Because the problem doesn't give me a number for potential energy. I didn't break the work done by friction down though. How come? Because it gives me a number, so I don't have to. But I can't get rid of the m's because there is no m in there. So then I got to carry that algebra out. How do I get rid of the half? Multiply it by 2. How do I get rid of the m? Divide everything. So 2 times 1 half mv1 squared plus mgh1 minus the work done by friction divided by m, and then what? Square root this whole jabber right here. If you did that, your answer would come out to be what? Something less than 28.1. Think just didn't have a number? I don't need it, nor do I want it. I just don't make it something else. I would much rather spend the last 3 minutes here doing something different. And the something different has to do with the second part. Because remember, if my change in energy is equal to the net work, how do we calculate work? Yeah. F times delta x, or F times D kind of in this case because it's kind of slanted, right? So that net work for friction would be equal to the force of friction times the distance traveled. So the second part of this question, what's the average force of friction acting on the cart on the way down? Well, that's the work done by friction divided by the distance. Right? So since the work done by friction is equal to the force of friction times V. The work done by friction divided by V is equal to the force of friction. Special note. Now look, you know a little geometry, right? This is 40 meters. However, that's not the D. Because friction doesn't do work over the 40 meters. Friction does work over the entire distance along the track, which in this particular case is how much? 55 meters. You know, so I go over here, right? It's easy to take a look, right? This is some height, but friction is doing work along this distance. So make sure we understand we have different distances involved here. And then our last question for the day, it's been a really good day. What is the average friction force? That's not a word that we've used too often because most of the time our forces are constant. How come we're using the term average slash? Why is the friction force not constant?
Because
The angle isn't constant. Remember, what's friction force? Mu times the normal force. Look at the normal force here. Here it's pointed straight up. So here it's pointed that way, that way, that way. It's always perpendicular to the surface, right? If that normal force is perpendicular to the surface, it's going to change, and therefore the friction force is going to change. Right? It's going to be very difficult for us to get to that level of calculation, but we can take the average with respect to all of that.